Welcome to this course on nanostructured materials, synthesis, properties, self assembly and applications. Today we are in the module 3, lecture 10, and we begin a series of 3 lectures on core shell nanostructures. So, today is the first lecture on this 3 series part lecture series of core shell nanostructures, and that belongs to the module 3 lecture number 10. Now, what are core shell nanostructures? These are particles that contain an inner core covered by a shell. Now, the inner core can be of one material and the shell can be of a different material. So, why core shell nanostructures are important? They are important because they give improved physical and chemical properties over their single counterparts. For example, if you have a core of a material A and a shell of material B, then the core shell of A and B can give you improved reactivity on the surface, can enhance the stability and dispersibility of the colloidal core, and they can be used in many applications. So, what are these applications? There are diverse applications in medicines, for example, in controlled release of drugs, in drug delivery agents. They can protect materials from light and moisture sensitive compounds. So, if you have a moisture sensitive compound, you can make it as the core and you can cover a shell which will prevent the reaction of the atmospheric oxygen or moisture on the core. So, you can stabilize the core material. Then you can use them as catalysts, as coatings. Several applications are there for core shell nanostructures. Now, the synthesis of a core shell nanostructure can be followed on basic principles, which are the miscibility of two materials and their interfacial energy. That is very important when you design a core shell nanostructure. If they are immiscible, significant possibility of the formation of core shell nanostructures are there. However, if they are miscible, then they may form a solid solution. So, this immiscibility is important. Now, if you have a large interfacial energy, then you get individual particles. So, you have A and B and you want to make a core of A and shell of B. If the interfacial energy between the A and B material is very high, then chances are that you will not get a core shell material, but you will end up with two materials, one A and one B, and such a material will then be called a composite material. It will not be called a core shell material. So, large interfacial energy is not good for core shell nanostructures. Then if you consider lattice mismatch, that refers to basically the lattice parameter of two materials A and B. If the lattice parameters, that is the unit cell parameters, are widely different, then that will increase the interfacial energy, and thus you have to choose materials which do not differ significantly in their lattice parameters or lattice constant and should be within 1 to 3%. So, if you have large changes in lattice mismatch or large lattice mismatch, then that will increase the interfacial energy, and that in turn will make it difficult for you to make a shell on top of the core, and you will in turn end up with two different types of particles, which is a mixture, and then it is called a composite. Now, how do you achieve uniform core shell structures? If you slowly add the shell forming agent at relative low temperatures, that is important, then the sequence of mixing of the reagents, how if you want to make A on top of B or B on top of A, the sequence of mixing of the reagents which are related to A and B are important. The proper choice of shell forming agent is important. For example, if you want to make a shell of silica, then you have to take appropriate reagent which contains silicon. For example, some alkoxysilanes like ethoxysilane, methoxysilane, they will be used for making the shell. So, appropriate reagents have to be taken which will be related to the shell forming agent. Then the rate of addition of the shell forming agent is important for making a proper shell, and the control of the temperature and the selection of organic ligands which adhere to the surface of the core. So, these are some of the key parameters which one has to take into consideration when one is planning to form a uniform core shell structure. So, there is thermodynamics and there is kinetics both involved in making a stable core shell structure, and of course, by changing parameters you can sometimes get metastable phases and you can stabilize those which normal thermodynamics will not allow you to make them stable, especially because you are making the synthesis in the nano dimensions. Now, some of the mechanisms which lead to the formation of core shell structures. Typically, core shell structure is represented like core with this symbol which is at and shell. That means, whatever, suppose you are making A is the core. So, you write A at B where shell is B. Now, there can be several different mechanisms by which you can form core and shell. So, here for example, you have a particle which is going to be your core material, and then you want to make a shell of some other material. So, if this material and this material come close and they start agglomerating on the surface, right, you can make a shell like that. So, you can do what is called direct heterogeneous nucleation and growth. So, you have this A reaction showing you direct heterogeneous nucleation and growth, and it can form a seed. Then on top of that you can make a shell like this. So, first you can have one layer which can be kind of a capping layer, and it forms one black layer on top, and then you have a material which can be put on top of that capping layer. So, here you have the core and then the capping layer and then the shell. However, you can directly make a shell on top of a core. If you have a rod like particle, you can get rod like core shell structures. Then you can also have suppose you have this is the example of zinc sulphide. If you have zinc sulphide or zinc in the wood side structure or zinc sulphide in the zinc blende structure, depending on the two structures, since they are different, the shell will form in a different manner. For example, if you take woodsite type zinc sulphide and you are trying to make a shell on top of it, then you normally get this kind of a rod shaped structure. When you take zinc blende, typically you get this kind of tetrapods. So, the shell adapts to the symmetry as well as the shape of the starting core. So, that is what is shown here. So, here the core is anisotropic and the shell which forms on top is also anisotropic. Here the symmetry of zinc blende and woodsite is taken into consideration when the shell forms. So, on woodsite you get an anisotropic structure, whereas on zinc blende you get a tetrapod like of structure because of the tetrahedral symmetry. So, the symmetry is important and the shell adapts to the symmetry. Now, you can also have a 3-step shell growth process. Example, in an organic media, here you are making a silver shell on a particle. So, you are adding some silver nitrate and then you are making this shell on top which is initially amorphous, and you add some other alkylating agent. So, you do some cation exchange on top of that, and you can remove the silver, and you will get this shell which is favored by the strong acid softness of silver plus. So, then you can get this kind of coverage on top of the core. So, you can have a 3-step shell growth process in organic media, the way it has been explained, using first a silver shell which forms then an amorphous silver sulphide or shell on sulphidation, and then you can remove the silver ion and you can exchange the cation with silver, and then you get a different shell with this sulphide on top of it. So, this kind of 3-step shell growth process is possible in organic medium. Now, this is another process by which you can get core shell structure. So, it is a controlled hydrolysis and condensation reaction in organic medium. So, you supply a metal alkoxide, it can be silicon alkoxide or titanium or zirconium, and you have a core particle, and then you build this kind of structure on top of the core, and then you have hydrolysis and then condensation, and then you get this kind of shell formed on top of it. So, this is one mechanism. You can also have a sacrificial mechanism, where you start with a particle and then you some of these exposed layers of the starting core are removed, and these particles come on top of the inner core. So, the core diameter you see here, it gets reduced in the core shell structure. That is because part of the exposed layers have been removed during this reaction, which may be a redox type of reaction, and ultimately the core diameter is smaller than the starting nanoparticle, and the shell is of course formed by the new material which you have started, and this can be done by a galvanic replacement reaction in a cell, and you can see these particles which are going out is actually belonging to the core material. So, the some of the particles are removed from the core material, and the incoming material is deposited on that inner core, ultimately giving you a smaller core size compared to the starting material. So, this is called a sacrificial conversion of the core material. Now, there are other methods or mechanisms by which you can get core shell nanostructures. For example, this is a very famous method, and the effect is called the Kirkendall effect, where you have a core and you form a shell on top using this kind of redox reaction or a sacrificial reaction, and then you have the Kirkendall effect, where it is an atomic diffusion process which takes place through vacancy exchange without having a direct interchange of atoms. So, there is a vacancy exchange. Once this core shell is formed, then you basically there are fast diffusing species in the inner core, and the outer region acts as reservoir of slow diffusing species, example metal cations and oxygen anions in oxide passivated metallic nanoparticles. So, what you can get using Kirkendall effect is you can get a hollow structure, or you can get a core shell kind of structure like this. So, in this Kirkendall effect, you are basically taking the process is through vacancy exchange rather than direct interchange of atoms, and there is a net transport of matter from the core outwards along with coalescence of the vacancies into a large void. So, these vacancies they start moving, and the vacancies all kind of coalesce together to form this gap between the core and the shell, and you have that matter transport is towards the outside. So, net transport of matter from core to the outward direction takes place in this Kirkendall effect. Now, you can also have a self controlled nucleation growth. So, the energy activation barriers for the homogeneous nucleation of individual compounds may diverge such that two different materials form at distinct times or temperatures. So, initially you may have one particle, and so that forms the core, which is the fast reaction from a system of two types of species. One you can see is light gray, the other one is the dark one, and what happens is the lighter ones aggregate faster and you get a core particle, and then the darker ones aggregate slowly. So, they form on top of the light gray sphere, and so they form the shell. So, this is a self controlled nucleation and growth mechanism, and it has two different materials which form at two different times or temperature, and the shell material is produced exclusively by heterogeneous nucleation on the in situ formed seeds. So, this is the seed, the light gray particle which is formed in situ from these small light gray particles. This acts as the seed for the formation of the shell, for which is denoted by these dark small spots, and so you ultimately get this dark shell on top of the light gray sphere. So, this is by self controlled nucleation growth mechanism that you can make a core shell structure. So, there are many ways by which, as you see, you have already several methods forming core shell structures from seeds using heterogeneous nucleation and growth mechanism, then a 3-step shell growth mechanism, then controlled hydrolysis and condensation reaction, sacrificial conversion of the outermost layer of the core, then the Kirkendall effect giving you movement of particles or matter from the inside towards the outside, leading to this vacancy, coalescence, and ultimately leading to this hollow core shell structure. It may be completely hollow if this continues, and this is an intermediate structure. This is the final structure where all the matter has moved from the core to the shell. Then you have self controlled nucleation and growth. You can also have thermally induced phase segregation and solid state diffusion. So, you have two types of particles here, and then it forms a composite particle, and then as you heat them, this composite particle, as you heat them, the phase segregates, the dark ones and the white ones segregate to form two completely distinct entities. One forms the core, the other forms the shell. So, this is thermally induced phase segregation and solid state diffusion. Here what happens is you have a core particle and there is another particle, and initially they adsorb on the surface. So, you have these small particles becoming larger, they are coalescing on the surface, and ultimately you can form a core shell type of structure. So, several mechanisms of making core shell structures. Now, we come to a very important thing, that how do you look at these core shell structures. Finally, once you make the core shell structures, you have to show that they are core shells. So, how do you look at them, and that is very important in this kind of science or technology, where once you have made these nanostructures, how do you exactly identify the core and the shell. The basic technique which is used to characterize these core shell structures is by electron microscopy, and in electron microscopy you use basically the TEM, which is the transmission electron microscope, and then in the transmission electron microscope you can do several things. You can image the nanostructures, or you can do electron diffraction and find out the crystal structure of your nanocrystals, and you can also find out the composition of your nanocrystals by looking at what we call the energy dispersive X-ray analysis. So, all these things can be done using a transmission electron microscope. So, this is an example of a core shell structure where you have cobalt iron alloy as the core particle, and you have iron oxide which is the shell. So, this is the high resolution transmission electron micrograph, which is showing the crystalline shell around a core. So, the core is at the center, which is made of cobalt and iron, and the shell is made up of iron oxide Fe3O4. And how do you make these particles is that you start with cobalt ferrite COFe2O4 and use oleic acid and oleal amine, and then phenyl ether and iron carbonyl. If you reflux it, you end up with the core shell nanoparticles of this kind. This is what you see in the image, and if you see the scale here, this is 10 nanometers, and so this particle diameter, the core shell diameter is around 10 nanometers, and if you look very carefully, then the core is here, and this diameter of the core is around 4 to 5 nanometers. So, what you can say from this transmission electron micrograph is that the core has a diameter of around 5 nanometers, 4 to 5 nanometers, and the shell thickness is around 2 to 3 nanometers. And what is in the core and what is in the shell, if you want to find out, then what you do electron microscopy by passing the electron beam through the shell and also through the center of the particle. When you pass the electron beam from the shell, then you get a spectrum and you analyze the spectrum. This is the energy dispersive X-ray analysis, and when you do, you can identify these peaks as belonging to various metals. So, what you see here is you can see copper, iron, oxygen, carbon. Now, copper is coming because you have used a copper grid to mount your sample. So, the copper does not belong to this material, but you are getting this copper line because it is mounted on a grid for holding your sample, and that grid is made of copper. So, you can ignore this copper peak. What you have to see is the other peak. So, iron is there, oxygen is there, and some carbon. So, carbon and oxygen normally can come as either oxide and carbide, or most of the time carbon comes as an impurity. Okay. So, what you can say is that the electron beam, when it passes from the shell, it can see carbon, oxygen, iron and copper. Out of that, carbon is an impurity and copper comes from the TEM grid. So, the material is made of oxygen and iron, and hence the shell is Fe3O4, which is what you wanted to make. So, you can confirm that the shell is Fe3O4. Now, when you do the same experiment with the electron beam going through the center of the core shell structure, and if you analyze the spectrum, you will see that the peaks correspond now to carbon, iron, oxygen, cobalt and copper. So, carbon and copper we ignore because carbon is an impurity and copper is from the TEM grid. So, what you find is that you have iron, oxygen and cobalt. So, when the beam goes through the center, you can say that cobalt is certainly at the center and iron is also possibly in the center, but iron and oxygen are certainly in the shell because that you already found out. So, from the EDAX what you can say is that the core is made certainly of cobalt, but it can also have some iron and it can also have some oxygen, because that distinction you cannot make just by using this EDAX analysis. You have to do some other methodology. What you have to do is called depth analysis. That means, you have to remove the surface and then study, and then you can actually identify the real composition of the core. Now, you can also do electron diffraction, and from electron diffraction of the core shell structure you get particular spots, and these spots can be identified with the Fe3O4 structure and also belonging to the alpha phase of iron, which can be due to the core which is made up of cobalt iron. So, using electron diffraction and by assigning these reflection, each spot is from a plane in the lattice, crystal lattice, and when you can assign the planes of both the core and the shell, you can say that both these are present in the solid. So, using electron diffraction you can assign both the structures which you see in the core and in the shell. Now, let us do some examples of core shell structures, and you can choose many thousands of examples of core shell structures which have been synthesized over the last 10-15 years, and we will choose some selective examples to give you a feeling of the type of core shell structures that people are discussing today. So, first, one of the most important shell making substances is silica, SiO2. Why people choose silica is because of easy control of deposition of the silica shell. Then you can control the porosity of this shell. Silica is optically transparent. So, whatever you put in the core, if it is an optical material, you can harness the optical properties of the core when you have a silica shell. Silica is also cheap. So, it is a low cost material to tailor the surface properties while maintaining the integrity and the stability of the core. Where are silica nanostructures applicable? So, there are a lot of applications of silica coated nanostructures. They are used for biological applications. The silica encapsulated nanomagnets have found applications as in biomedical science, and they can enhance the stability and luminescent properties of bismuth sulphide nanorods. These are few of the vast number of applications that you can expect from a core shell nanostructure, which has a silica shell on top of some particle. That particle can be a metal particle, it can be a semiconducting particle, or it can be an insulating particle. So, there are many examples on which silica has been coated to act as a shell. Now, this is a typical procedure